All right, let's start. Do you have any questions? All right. So we were still discussing the list of basic discrete random variables last time, right? And we're almost done. So let's list them again. So the name, right? We have the probability mass function, right? And then let's say expectation and variance, right? And so the first thing is Bernoulli. So here, right, one with probability P, 0 probability 1 minus P, expectation P, variance 1 P minus P. So, and then we have the binomial NP, x equals to K, and choose K, P to K, P minus K. Here, K runs from 0 to N. Expectation is NP, variance NP minus P. We have a Poisson lambda. And mass function is e to mass lambda, lambda to K over K factorial. Here, K runs from 0, 1, 2, etc., right? There's no upper limit. Expectation lambda versus lambda. Then we have the geometric, right? P, and then here is 1 minus P to the K minus 1 and times P. Expectation is 1 over P. Variance is 1 minus P over P squared. Then we have the negative binomial, right? RP, probably x equals to K is R minus 1, choose K minus 1. And then P to the R, 1 minus P to the K minus R. Expectations R over P. Variance is 1 minus P over P squared. Okay. So there's one more, right, called the hypergeometric. And then, sorry. So here, K runs from 1 to, etc., right? Here, K runs from R plus 1, etc. So there's one more, right? And which is the hypergeometric, and then we'll be done with the list of discrete random variables. But so one more time, right? So these are not only models, right, of certain thing, they're also kind of connected, right? related. So for example, binomial, right, is the sum of n independent Bernoullis. Negative binomial is a sum of n independent geometric. And Poisson, right, is an approximation of binomial when p is small and n is large, n times p is equal to lambda, right? So um, so the point, right, is that when you recognize these random variables and you can apply, right, the model that these random variables represent to a situation, then basically you can use the calculations that have been done to facilitate, right, your computation and your work. On the other hand, as you'll see, right, in the problems we'll be doing today, you want to kind of not overdo it. In other words, you don't want to force, right, like a certain kind of problem into a random variable that you know about. It may or may not work that way. So sometimes you can use these as more like a template, right? That basically you're used to, for example, with the negative binomial, right? You know how the mass comes up, right? Basically, this is the number of trials until you see the first are successes. So that means, right, the last out of all trials, the last trial must be a success. And then the previous R minus, sorry, is K minus one, right? Choose R minus one. The previous K minus one trials, right? You choose R minus one of them to be successes, right? So R minus one successes here, one success there, together is R successes, right? And then that's how many ways you can have R minus one successes in the previous K minus one trials, and then the last success, the last trial being a success. That's just a probability, right, of R successes, K minus R failures. But basically, right, that kind of argument can be used to do other problems that are similar to a negative binomial, let's say, right? And but if you insist that a problem must be of a certain type, then it may not work that way. Okay. So these are very, very useful, but don't overdo it. And you have to kind of watch what you have to make sure that you apply the model appropriately. So let's see here. So let's start with a question. So this is number 67, right? So the rate at which people are hit by lightning in a certain state is 1 per 100,000 people per month. A, find the probability that in a city of 400,000 people within the state, eight or more get hit by lightning in a given month. Okay, what's the answer here? Or rather, right, there's no, I mean, single simple answer, but what's the procedure? So first, right, this problem refers to a binomial, right? Example with n very large and p very small. So it's a Poisson, right? Situation with lambda being so 1/100,000 times 400,000, right? So the random variable we're looking at, which is the number of people get hit by lightning in that city, right, in a month, if you will, then that random variable is Poisson lambda, right? Poisson 4. Okay. So therefore, right, probability of x being equal to 8. Now there's no, I mean, you can sum everything from 8 to infinity, but again, right, that is an infinite sum and there's no easy way to calculate it. So, I mean, easy as in like precise way, right? Besides like using some sort of, well, actually, the way is to go with 0 to 7, right? Of e to minus lambda, lambda to the k over k factorial, right? I mean, theoretical answer from a to infinity or 1 minus this is fine. But in practice, right, again, this will be a practical way to calculate it, while the infinite sum, you have to stop it at some point and always incur some kind of error, right? Any question? So B, find the probability that there will be at least 2 months during the year that will have eight or more people hit by lightning. Okay, so how do we do this?
You stick the probability that you get from the Poisson into a binomial where we have
Right.
12 months and 12 n is 12 and then p is the probability of x greater than equal to 8 from the Poisson.
Correct, right? If you let y be the number of months, right, in a year, right, with 8 or more hit, right, then y, the setup of y will be, right, a binomial 12p, where p is probability x bigger than or equal to 8 in part A, right? So again, that's sort of like that model thinking, right, that you recognize that that's a binomial. Therefore, probability y bigger than or equal to 2, right, will be 1 minus, right, y equal to 0 is 1 minus p, right, raised to the 12, and 1 equals to 1, like that. Any question? Okay, so C, well, what was it? Counting the present month as month 1, what is probability that the first month to have 8 or more hit by lightning is month I critical one. How do we do this?
This is geometric with probability that we found A.
Right, exactly, right. So you let Z be, the first month, right, with 8 or more hit, then Z will be geometric P. So therefore, right, probability Z equals to I is 1 minus P, I minus 1 times P. Like that. Okay, once again, right? Model thinking. So this problem, right, sort of has three random variables incorporated, right, into the question. So like that. Okay, any question? All right, let's do the next one. This is question number 75. So two teams, right, play in a series. First to win 4 games win the series, right? And suppose that one team, right, is just stronger. So team, we can call it team A, right? Wins each game with probability 0.6. Okay. And then independently of the outcome of any other game, right? And then, so we want to find the probability for I equals to 4, 5, 6, or 7. So that's 4 questions, right? That the stronger team, which is team A, wins the series in exactly I games. Okay, so let's put it that way. That's 4 questions, 4 probabilities. I just wrote it in one statement, but so how can we do this? So if you let X be, right, the number of games that team A wins the series in exactly, right? Exactly X games, right? And what's probably X equals to 4? Should be that, right? Or no, X equals to 5.
5 choose 4, 0.6 to the 4, and 0.4 to 1.
Not 5 choose 4. That's wrong. Right,
choose
because 4 choose 1. Or 4 choose 4, whatever. Oh, sorry, 4 choose 3, right? The 4 choose 3. The reason is what? The last game must be a win for team A. Agree? So it's within that context, right? That we just have to read into the context to see, and I hope it's clear, right? Because first team to win 4 games, right, wins. So the last game must be a win. Therefore, either 4 choose 1 for the game that's lost, or 4 choose 3 for the 3 games, right, that A must win in the previous 4, and then 0.6 to the 4th, and then 0.4, right? Is it okay? And we can see what this is, right? So 6 is going to be 5 choose 4, right? And x equals to 7. 7 choose 5. 6 choose 5. You know what? I'm being crazy, right? Just 5 choose 3. And then 6 choose 3. Are we okay? So again, right, all of these are the 3, that's the 3 first games, right, that teammate must win. And then the last one is a win. Okay, so far? All right, so here's a question then. What does X remind you of?
Negative binomial.
Uh-huh. So is it a negative binomial? Is it a negative binomial? Answer? No. Because can X be 8 here? Can X be 9? No, right? First out of 4 wins. Sorry, first to win 4 games wins. Of course, assume that the game doesn't end in a tie, which is, I guess, the assumption here. You can play at most 7 games. Agreed? And so what's going on with X here? Notice X only represents, right, team A wins. What's the other possibility? Team A loses the series, right? Which may be captured by X, but not with a numerical value. So you could say something like X equals to infinity. And infinity here is just symbolic, okay? Infinity here means A loses the series. Are you okay with that? So again, I mean, it's just a notation, because if you throw infinity here like that and you calculate expectation, then that's not going to be quite appropriate, right? Because, infinity, throw in, add anything will be infinity. What I'm saying is, like, X by itself, right? All the states do not capture all possibilities that can happen, right? A can lose a series. We're okay with that? So in that sense, right? Or I don't know. I mean, I'm not sure if 0 is a more appropriate thing to put here, but A wins the series with 0 game. Not sure what that means. But right, there must be a part where A loses the series. What that means, right, is that this is like a negative binomial, but not a negative binomial or an variable. Okay? So that's what I mean by don't get too carried away with models. We use the negative binomial thinking to come up with these numbers. But by itself, the way we define the random variable doesn't have to be exactly that. All right. Any question?
Is it
So with
possible
that,
to restrict the range of X to make it fit this distribution? Okay.
you have to, well, you have to be more clear on what that means. Because for example, I mean, let's say you have in mind something like a binomial NP, 10 trials, okay? And what do we mean when we say that we restrict the range to 2 to 8? Well, there's a way. That means that's conditioning, okay? You can condition on this random variable being between, let's say, less than or equal to 8. But that's sort of not what we're discussing here, okay? We're not saying that we know how many games A needs to win to to play to win the series. We don't. Well, in a way, right? You see, that's what you're kind of thinking about. So that's why you say that you restrict the range, but not in that sense. In the sense that it's not the negative binomial conditioning on a negative binomial less than equal to 7. The reason is, again, right, the negative binomial only describes the number of trials you take until you get to how many successes. But naturally, here X only describes the winning scenarios and not the losing scenarios, right? So in that sense, it's not really about restricting the range in the sense of conditioning. It's just something else. Basically, it's missing a state. That's what it is. Yeah. So yeah, yes, it's an appropriate question to ask. Absolutely. But you got to be clear. You got to be clear on what you mean by restricting the range. If by restricting the range of values, you mean conditioning, then X is not really a negative binomial conditioned. X is just a negative binomial, but cut off, right? And then leaving the rest, and you call it some state.
I see. Thank you.
Yeah. Anything else? Yeah, so I think, right, to demonstrate that, just to go on with that thought, right? And I think infinity here is appropriate, but depends on how you look at it. For example, suppose you ask the expected number of games A plays to win the series. Okay, let's say you have that question. Would that be the average of these? Like this times this times this times this. If you ask, right? And this is not in the problem, but if you ask the expected number of games A needs to play to win the series, will it be like this? Well, the answer is not really. Why? Again, because there's a possibility that A loses the series, right? When you ask the question, the expected number of games A needs to play to win the series, you somehow know, or you imply that you know that A wins the series, right? Anyone who watched any kind of sports series would know that. You can't say that, oh, I know my favorite team will play, or I expect my favorite team to play this many games to win the series. Because I mean, they may not even win the series at all. Right. So in that sense, it also demonstrates that it's not really a negative binomial restricted. Because if that's the case, then expectation still makes sense with it. Right. But here, when you say expectation of the number of games needed to win the series, it sounds weird because you can lose a series. So basically, it's a random variable, but there's a state that is not being listed, right? That is not a numerical value because it doesn't describe what you're describing. Okay. So with that said, right, let's go back to the Banach, right, matching problem that we looked at last time, right, but did not finish. So what's the problem? The problem is about, a person, a mathematician, whatever, right, with two boxes of match, right? On the left and on the right, both initially contain n matches, right? And then equally likely, right, to select each box, right? And you want to find the probability that, right, the person reached into one of the box, found it empty, and found the other one to be K remaining. All right. And now, of course, when you look at these, right? So the first thing is you kind of want to run through the values to see if this makes sense. But anyway, right? So let's try to see. For example, when I read this problem, the first thing that jumps out to me is the 0. Is it really possible for the person to found one box empty and there's 0 remaining on the other one? Does it kind of contradict the language of the problem? I mean, is 0 even a possibility here? Or is a legal state here? Because, right, 0 means the other one is also empty, right? I mean, answering these questions will clarify the intention of the problem for you. Well, the answer is yes, it makes sense if you read the problem carefully, right? So the key is that the person found the box empty. So let's clarify, right? How many times does the person reach into this box, the empty box?
N
The person
times.
would reach in, not n times, n plus 1 times. And that's the key. because n times, right? The nth time they will still find the box not empty because there's still one remaining. Do we understand? So that's the key, right? Basically, found mean discovery, meaning that they really reach into the empty box n+1 times. That's one of the key to pay attention to, right? That's language. All right. And also, right, there's something special. Okay. And also, of course, right, there's just a slight confusion between the left and the right, because here the language doesn't say that. So for now, right, let's just really separate our left and right. And let's say that this is a probability that you found the left empty and the right containing. Okay, right, remaining. Okay, let's do that. Then you see, right? So first of all, how many times does a person reach into the pockets total, left or right included? It's called total trials.
n+1 plus n minus k.
Correct, right? So n for the left, n minus k for the right, and then 1 for the last one to reach into the left pocket to find it empty. And it's sort of in that sequence in the sense that this one must be the last action. Does it make sense? To find the left empty. Okay. Because, right, what does that remind us of? A negative binomial, right? Where okay, so you see, in this sense, then the left reach is a success, right? And the right reach will be a failure, whatever that means. It's not really a success in whatever sense, right? It's just really that's a special place that we kind of, pay attention to. Does it make sense? So out of 2n, right? So out of 2n minus k plus 1 trials, we want the last one to be a success, right? The last one to be the reach into the left. So out of the previous 2n minus k trials, what do we want? We want to choose n times the person reach into the left pocket. Agree? And then the remaining one is easy because it's 1/2 each. So it's 1/2 rates the total number of trials, which is 2n minus k plus 1. That's all there is. But not yet, right? Just one last bit of detail, which is that we're looking at left and right here, right? So meaning we specify this, but we will need the, one box empty, the other one k remaining, right? So what do we do with this? Since the left and the right box are symmetric, right? We can swap the right and left and then have the same probability. The final answer is going to be double this, right? which is really 2n minus k, 1/2 raised to 2n minus k. Any question? So that's the classical Banach matching problem, right? My point, right, in demonstrating this problem is that you see, is this a geometric random variable? Who cares? I mean, well, it's not really, right? I mean, if you really spend time identifying this to some geometric, sorry, not geometric, negative binomial random variable, then you probably will have a hard time and you'll be confused and it's not going to go anywhere, right? The key is to use a negative binomial similar analysis to a negative binomial to write down, right, the total number of trials, the last one to be a success, and then place, right, the previous ones, right, and then select so many successes, etc. This way of thinking is definitely negative binomial thinking. But is it really a match for a exact negative binomial random variable? I don't think so, right? Because here, again, is capped, right, by n. It doesn't go to infinity, which is exactly the same as this one, right? So sort of this scenarios, right, is what, who knows, makes probability maybe a little bit hard, right? You have to know which model you're writing down and why, and not to kind of go overboard, right? With say, oh, that must be a negative binomial, blah, 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 because it's not really the case here, right? It's just these numbers within this possibilities. Why? Because this is the thinking. Okay, any question? All right, so that's the Banach matching problem. So let's try to look at the, so this is quiz 3. The number, question number 80, right? So they ask you to basically resolve the Banach matching problem. But the moment is when the first box is empty, as opposed to being found empty. And you probably, right, understand what this means. And then the other box, right, contains K matches. What would that be? So what's the difference between this one and the Banach problem proper?
Main difference is that we don't have to take a look again in the empty box.
Yeah, right. It just really changed the number of trials, right? So here, the original Banach matching problem, you have to reach into the empty box, right? Whatever that box is, let's say the left one, n+1 times. And that's probably the weird one. We naturally think n times. So in some weird way, right? This question is what we would probably think of when we read the Banach problem the first time. But so, right, the main difference is now we reached into this box n times only, meaning that everything is done with, you know, like that, and then we have to subtract one here, right? So the answer is something like, right, if you separate out, if you distinguish the left and the right pockets, right, then the answer will be 2n minus k minus 1. Choose n minus 1, right? And then 1/2 to the 2n minus k, right? Again, because you only reach into the left box n times. So the previous n minus 1 times must be reserved, right? Sorry, out of the previous 2n minus k minus 1 times, choose n minus 1 time to reach into the left box. And then, of course, you double that because left and right are symmetric, right? Like that. Any question? Okay. So I hope, right, that gives you a flavor of, you know, negative binomial and geometric thinking, right? So let's move on to our last random variable of the discrete family, which is the hypergeometric. And the hypergeometric has 3 parameters. So let's describe it. So the hypergeometric, so first of all, what's the scenario? The scenarios, well, you can have a generalized hypergeometric, but the classical geometric is hypergeometric is an urn with 2 types. Usually you can call it red and blue, you know, balls, black and white, whatever, right? Let's say white and black. There's so many types in the white. Let's say M, and then the remaining are black. And so it's given however you want it. But here, right, the total is given. So if M is white, then N minus M is black, right? So that's a composition inside the urn. Then you select without replacement, right? It's without replacement, a sample, right, of size n, little n, okay? So that's the experiment. You basically just select without replacement, right, from an urn with 2 types. And the random variable that you're interested in is the number of you know, the first type, say white balls, right? In the sample. That's it, right? So it's a bit long to describe because you have to give the numbers for the first type, second type, and the sample size. But really, right, it's just about selecting without replacement from a urn, right, from a finite population, if you will, with two types, and you ask how many presents, right, of the first type in your sample, right? Okay. So let's see here. What values can X take? So where are we on quiz 4? So let's work this out, right? What's the support of X? Of course, right, in terms of these numbers. What's the support? What values can X take? Well, certainly can take values 0, right? 1, etc. What's the maximum value it can take? So here, right, it's not clear unless you have the actual numbers in front of you. Basically, the number of white balls, right, cannot exceed the sample size, but it can also not exceed, right, the original number of white balls in the urn either. So it's the minimum of the two. Okay, so far? Now, in terms of the masked function, what's the probability X takes on any of these values? Well, it's your good old counting problem, right? How many ways can you select a samples of size n? Is big N to small n, right? How many ways can you select k white balls out of this? Well, it's m choose k, right? The remaining must be black. N minus k, like that. Okay, so far? So now, what's the next thing we should ask about a random variable? We have a hypergeometric, we define a random variable, right? We show is probably a mass function. So next thing to do is to compute is expectation, right? So if you go with definition, the expectation will be the sum, right, over all range of values, which is from 0 to this, of k, the value, times the probability, right? X takes on these values. Well, the point though is, can we simplify this? Do we know what this is? Well, let me tell you, right? And again, this is exactly why we memorize stuff. The answer is actually much simpler than this sum. The answer here is actually very intuitive. It's going to be little n times big M over big N. Okay. So never mind how this is found. You can look into the textbook. But the first thing is, do we know why, or at least do we see intuitively why this is true? Or what does that supposed to represent? M over big N represents the ratio, right, of white over the total population, the total number of balls, right? So it's really the ratio, right, of the white balls inside the earth, right? And then you select a sample of size little n. So this is very much of the type of n times p. Except, right, don't be misled by this in the sense that it's really just a mnemonic. It should just guide you in memorization, but it's not really, right, the n times p of the binomial. Because what's the difference? The difference, right, is that this sample, right, the color of the sample are not independent. Because if the first one is white, then the second one, right, the chance of being white will be smaller because there's less white now in the urn, right? So the colors influence each other. The sample, right, they're not independent, the outcomes. If you select with the replacement, meaning you select a ball and then you note the color and then you return, then it will be a binomial, right? The colors will be independent, but this is not. But the result, as far as expectation is concerned, still follow that route, n times p. There's a reason for that, but the reason, but do not mistake this for our independent trials. Okay. Any questions so far? So let me give you a reason, right? And reason in this class, as far as I'm concerned, the reason that's worth knowing in a probability class are probabilistic reasonings, right? I mean, I'm not saying that these are not interesting in of itself, but this kind of reasoning, or if you're interested in this kind of reasonings, they belong to a combinatorics class, right? The trick of manipulating combinatorics expression to get out to something should belong to a combinatorics class. In a probability class, we would do, right, probabilistic argument, which should be easier or more intuitive, right? And the reason here is a very, let's say, how to say this, very distinct probabilistic argument, meaning that is everywhere. And it's like this. You denote, right, for the sample, there are n, right? There are n balls. So you let's say, xi represents the indicator of the ball I in the sample. Okay. So basically, again, this is the indicator function. You go through the balls in the sample. And if it's white, you count this one, right? And if it's not white, you don't count it. Why? Because the x here, which is the total number of white balls in the sample, will be the sum of the xi. Okay. And this technique, which is very, very common in 478, right, is called, whatever you want to call it, decomposing a random variable, right, a total, into its component of indicator functions. Okay. What's the advantage? The advantage is, remember that expectation of a sum is the sum of expectation regardless of how the random variables interact. Here, right, the random variables, in contrast to the case of the Bernoulli, the geometric, right, that when we say they sum out to be the binomial or the negative binomial, those are independent. Here, the xi's are not independent. Okay. Because if you know some balls is white, it influences how the other balls being white or not. However, right, that's the beauty of expectation is it doesn't care if the xi's are independent or not. It's just linear. And so we can pass this inside the sum. But once you move inside the sum, then you can just focus on each xi itself. All right. And then from the point of view of the ball I, it will be white with probability m over n. Okay, that's it. And the little n of this, so this n, m over n. That's it. That's the argument. Okay. This is the argument by indicator function. One thing that might be, let's say, not easy to digest for folks new to this argument is they find it hard to transition from this to m over n for any I, because probably they recognize that these guys are not independent. However, right, you should think about this more carefully if you want to understand this argument. But here, each of the xi, when we look at expectation of xi, we are looking at it and it only, without any information on how the other balls come out. So when we say, let's say, the expectation of the fourth ball in a sample, fourth as in the sense of like, okay, that's ball number 4. But when we look at it or we investigate it, we do not have any information about the colors of any other balls in the sample. That's the meaning of this. And that's why, right, as far as we're concerned, it can be white with probability m over n. We don't know anything else. And that's how it comes out. Any question? All right, so let's write down the variance. For this hypergeometric, the variance will be n times M over big N, which is the one we're familiar with. But then there's this, there's this, there's this, there's this, there's that. And this is why I don't memorize the variance of a hypergeometric, because, well, there's some pattern to it, but the pattern is not worth memorizing. I mean, it's not worth memorizing, but the pattern is not something that intuitive, as in, right, the sample size times the success rate, right? Here is a more complex combination. So this is best reserved just to, look up or memorize without much understanding. I mean, there's some understanding to it, but I don't think this is something that illuminating. So this one, yes, right? But that one, nah. Any question? All right. So. Let's move on to the continuous random variable, which is chapter 5. Let me see if I want to offer you a proof of the following. So the only thing that the textbook mentions, which, I already told you anyway, but it's really a explanation of something. So let me say a few things, right? So there's section 4.9. So 4.8 and before, right, talks about the family of discrete random variables you should know. 4.9 talks about expected value of sums of random variables. And here they exactly talk about what I was telling you all along, that expectation of a sum, or if you will, even a linear combination, will be the sum of linear combination, right, of expectation for any random variables. Now, so I think the only thing that's worthwhile here is the proof of this. And the proof here is for discrete random variables, okay? So these random variables are discrete. Doesn't really matter, but so the proof is as followed. So the way you should look at this is that if you denote S to be the sum, right, of discrete random variables, linear combination, then S itself is discrete, right? In other words, we can write down the probability mass function of S for discrete values, right? Okay. And so when we look at expectation of the sum or expectation of big S, that's what we're after. Then by definition, this is a sum over S, right? Over values of S. Of like that, right? Of those values times probability that S takes on those values. Okay. Hold on. Let me see if this makes sense. Uh, right. Okay. Yeah, that makes sense. But then the next move, right, will be that you will. So instead of looking at, so where does these values of S come from? These discrete values of S, right, will comes from discrete values of the Xi, right, multiplied with the Ci. So in other words, for each value of the S, right, for each discrete value of S, there corresponds, right, the Cixi, these values of the Xi, such that the sum must be equal to S. Okay. So all we're saying, right, is just something very, very mundane. Like if you look at this random sum, right, and you look at the probability that the sum takes on some values, then those values must come from the contribution of the individual, right, Xi taking on the values that will sum up to those values. So in other words, right, these S right here, right, so this is the sum over all possible values, but the inside is the sum over particular values of Xi that would basically make up the X value, the S value. It's okay. So each of these represent a single value of the sum, right? But there are the Xi that would make up this sum. And here, right, the linearity, exactly because of this little sum and this probability, you can multiply, you can distribute this probability, which is a number inside the sum. So in other words, this is sum over all values, and then within each particular value, you can do that. Okay. And then you can switch the order of the sum. So here you sum over all values of the sum, right? And then you sum from 1 to n for each of the sum men. Here you can switch the order of sum to be sum over the sum men first or last, and then sum over all values of S first. And then you can factor out a Ci because the here is independent, right? And inside here, each of these will be expectation of Xi. Like that. Okay. So what I'm trying to say here, right, is just to give you some clue on why expectation can be linear. And the linearity, right, exactly comes from the fact that behind the scene, there's some probabilities that work for all the Xis. Basically, this probability, even though we represent it as like this, it's really probability of a outcome. like an outcome that s equals to small value of s, let's say, right? These outcomes. And this probability being of outcomes can be distributed, right, into the sum over the x over the I, because the sum is linear. And then you switch the order of the sum, summing over these outcomes first. Then that will become expectation over individual xi, individual random variable. So I just want to offer up this explanation, right? Just in case that some of you are, kind of curious on why, like this expectation is linear, right? Regardless of relationship of the xi. But if you just want to take this now by faith, let's say, and just focus on the application of it, that's fine, right? This kind of argument, again, belongs more in the kind of a measure theoretic argument, and so more kind of like appropriately reserved for a more advanced probability class. All right. So, having said that, let's move on to chapter 5. Continuous random variables. All right. So, five point one, introduction. So, the term continuous random variable should be understood as indistinguished, right, to discrete random variables. And so now we can, right, properly talk about the difference. So a discrete random variable then is support, right? The place where it takes non-negative probability will be discrete. In other words, is separate values, right? They're separable. Most of the time they're integers, but there's no rule that requires that they're integers. It could be 1.5, 2.5, that's fine. But using integers as representation, then basically they are separated, right? Like that. So they don't have, so basically, say even if you look at a continuous range of values like this, because you just want to write down, it will boil down to x being 0 and x being 1, because there's nothing in between. Okay, so it's discrete like that. On the other hand, for a continuous random variable, it will have continuous support. What does that mean? First of all, that means that the range of values you can take usually is over an interval, like 0 to 1 or 0 to infinity or minus infinity to infinity. Okay. Second of all, right, the probability that the continuous random variable takes on a particular value will be 0. And this right here is a hallmark of a continuous random variable. It does not, the probability that it takes on any particular value will be 0. Okay. On the other hand, the probability that is inside some continuous range of values will be positive as long as that continuous range of values is inside support. Okay. So, of course, we need more objects to describe how the continuous random variable behave. But the hallmark of it is continuous support, meaning that, right, it's over an interval. I mean, it doesn't have to, but you can think of that way. That's the best. The probability it takes on any particular value will be 0. But the probability that it's in a range of values, continuous values, will be positive. So let's look at an example. Just to give you some idea. Let's suppose that you have the interval 0 to 1. All right. And let's say you drop a needle, right? And this is a very fine needle. It has only 1 point, right? Onto uniformly, meaning arbitrarily, over this interval. Okay. Then you can be convinced that the probability that you hit a particular value, like 1/2, will literally be 0. Because, right, if you move continuously and you drop the pin, you probably can get close to 1/2, right, with some probability. But the probability you hit exactly 1/2 will be 0. Does that make sense? Because, I mean, one way to explain it is 1 point out of infinitely many points. Because all of these points can be hit, right? So a single point can be hit with probability 0. On the other hand, right, you can say that the probability that is going to hit between let's say 1/4 to 3/4, right? What's the probability you drop the pin and it's within these two numbers? Will be something. And let's say if it's uniformly, then it will be, right, the length of this over the total length. So that's 1/2. So that's an example, right? By the way, what I'm describing to you is actually a random variable, a continuous random variable called a uniform random variable, uniform 0 to 1 random variable, right? But basically, right, just imagine that you drop a pin onto a continuous range of values. Then the probability that you hit any particular value will be 0. But the probability that you are in any range of values will be the relative length of that value over the total length of the value. Is that okay? Any question about this? All right. So, by the way, right, let's just even throw it in now. Because the probability that a continuous random variable taking on any particular value will be 0, then this will actually also be equal to this. Will also be equal to this. Will also be equal to this. All right. So the difference, of course, is the equality, right, added on the ends. So with continuous random variables, whether it's an open interval or a closed interval doesn't matter in terms of the probability. Because the probability it takes on any particular value will be 0. But with discrete, right, that's not true. Right? Discrete random variables, you might go over a single value and you might pick up a probability mass because the random variable will take on that value with some probability. Okay. So with continuous random variable, you have the luxury, if you will, for not paying attention to whether you write less than equal to or less than. With discrete, you cannot. But in general, it's a bad practice anyway to not pay attention unless you know that you don't have to worry. Okay, but if you do know that the random variable is continuous, then whether you write like this or less than equal to doesn't matter. Any question? And so, right, the object to control or to understand about a continuous random variable is called the probability density function of a random variable. I mean, first of all, this will be referred to as PDF. It's just the name. When you hear PDF, that's probability density function. Denoted like this, but I would prefer subscript X, big X, to refer, right, which random variable we talk about. So little f for the density, little x for the value that we're talking about, right, the density at. We're looking at density at. And big X for the random variable we're referring to. Okay. So for example, right, you can have big F of X to be e to minus X. Like that. So this is a density of a random variable, the exponential random variable, if you will. But we'll look at that later, right? So what does the density have to perform, or what's the role of it? So let's talk about the requirement of the density. It has to fulfill two things. The first thing is it cannot be negative. It can only be non-negative, right? And you see that actually we only care where it's positive to begin with. But in general, it must be non-negative, or it cannot be negative. The second is that if you look at the area under the curve of this density, it must be 1. And again, this is the general writing because we don't know where the support is, but most of the time you integrate over the support. So, right, let's take a look at this. It's exponential, so therefore it's non-negative, right? In fact, it's positive. I mean, so you see, technically speaking, people can even define like this: e to minus x 0 and equal to 0 for x negative. That probably is the complete description, but no one really would write this down because it's understood that if it's not mentioned, the density is going to be 0 outside the range of description. Okay, so that's sort of like why the gradient equals 0. Second, right, let's check out the integral. So you see here, the integral only has to go from 0 to infinity. E to minus x dx, right? But of course, it's just minus e to minus x. And really, that, right, that's 1. Okay, sorry, just say 1. So the picture, right, of a typical density function will be whatever, but it's non-negative. And then the total area is 1. Any questions so far? So we talk about the density, its requirements. Now let's talk about the meaning of density. So first thing to remember, and it's very crucial, is that the density is not a probability. All right. In fact, it's very easy for you to have the density where the density values is bigger than 1. It can be done. It's easy. Okay. The thing is, right, again, it's non-negative, so it's similar to probability that way, but there's no upper cap. It can be bigger than 1. What's an example? Well, you can do something like this, right? Let's say you draw a triangle from 2 to 1/2. No, right? 2 to 1/4. Wait, 2 to 2. Wait, I cannot do math. Base times height divided by 2. So I want to have 2 times 1, right? Yeah, like that, right? So this and 0 everywhere else. This graph right here can represent a density of a function of a random variable. Because, right, it's not negative. The total area under the curve is 1. That's all there is. But there's some parts, right, that the density is bigger than 1. So the PDF does represent something similar to a probability called likelihood. But so it's true that, for example, the area of the high density is more likely to be visited or to happen than the area of low density. That's true. But you cannot read numerical value out and say that's a probability. Okay, that's the kind of the subtlety about this. Then what is the probability? So if X has density big F, little f, sub X like this, then the probability of A less than equal to X, let's make it more proper, doesn't really matter. A less than X less than equal to B, right? Like I said, doesn't matter about equality because it's 0 anyway, but this is the traditional way people write the probability of a range of values over a range of values. It's the integral from A to B of the density. And there you have it, right? That basically, if you integrate the density, you get probability. And that's the use of density is used to integrate, right, to get probability. Or if you take physics, that's exactly what density does. If you add density, you get mass. So if probability is like mass, then PDF is like density in physics, okay? It's the denseness, right, of the materials, right, along the line. So if you have a one-dimensional wire, then this graph describes to you the denseness of the material, right, along that wire, like that, okay? And so that also explains why, right, the total area must be 1, because that's the total weight, right, the total mass, which is the probability, right, that you take on any values from 0 to minus infinity. So that's 1. And density cannot be negative. Any questions so far? All right, so let's work with some basic examples, right, to see how this works. So what are we on? Quiz 5. So let's say that suppose X is a continuous random variable with density C times 4x minus 2x squared, 0 less than x less than 2, and 0 otherwise. Part A, what is the value of C? How do we find C here?
We know that the overall area of the f of x curve has to equal 1. So we just take an integral from 0 to 2 of that function.
Mhm. Good, right? That's exactly it. So we integrate this from 0 to 2, and it must be 1. So C literally is 1 over the area of this integral, whatever that is, right? So C, let's just write that down, right? I mean, abstractly, this is the answer, but of course you're asked to calculate that, right? And, well, what was it? So it's 2x squared, right? Minus 2x cubed over 3, right? So that would be 8, right? Minus 2/3 8. So that's 8 over 3, right? Okay, like that. So note that a lot of most of the times you can trust that people write down densities, they know what they're doing. But you probably want to do a reality check yourself just in case. I mean, outside of class, whatever, that this guy is non-negative, right? I mean, the C is there so that you can make sure that it integrates to 1. But if this guy ever is negative, then you know that you have a mistake on your hand, right? Anyway, so that's that. And by the way, right, it's a very common practice, not in this class, but in more advanced courses, to give density like this, especially in a class like simulation, right? Because in a simulation class, a Monte Carlo simulation, some of the point is to find the C itself using simulation. But anyway, the thing, right, is that the C is called the integrating constant. And the reason why C is very popular in more advanced courses is because you see that with density, what you usually are more interested in is the shape, because if it has some area, right, then you just have to scale it with a constant to get it down to 1. So sometimes the scaling constant is not super interesting to you, but sometimes it is. I'm just saying this so that you don't get hang up if you are given a problem with a C. I mean, you might get hang up in the sense that you are asked to find a C yourself, so you must know how to do the integral. But sometimes, like I said, the point is to work with the density without worry too much what the C value is. So, right, you have to see which one's which. For example, right, I mean, you should know, or most of you might have seen, right, the density of a normal random variable, let's say, right? So a normal random variable, this is the function part, and there's a constant part in front. Does anyone know what the constant is? This is just about knowledge, nothing more. The constant is 1 over square root of 2 pi sigma squared. Okay. So again, right, I'm just demonstrating that certain kind of constants, if you work a lot with a certain density, but sometimes, right, or the normal curve is about this, right? The constant is there to scale it down so that the area is 1. Okay. Any question? B, find the probability that x is bigger than 1. only answer should be straightforward, right? You look at the integral from 1 to 2 of the density, right? Which would be 4x minus 2x squared dx 3/8, which is 3/8 times 2x squared minus 2x cubed over 3, which is so 1/3, right? 8 over 3 minus 1/3, right? Sorry, 2 minus 2/3 is not 1/3. 2 minus 2/3 is 4/3. Hope I'm right. So 4/3. So that's 1/2. Which, right, sounds a lot like Calc 1, which it is, right? Again, don't get too bogged down with the calculus aspect. Well, you must be able to do calculus here, right? It's not like you can escape from calculus, meaning that you are expected to know integration and differentiation very well. But we're not here to do calculus per se. We're here to do probabilities. But so the calculus part is assumed, right? You must know it very well, including Calc 3, right? Which is going to be used in the next chapter. But right, I mean, this is just to demonstrate, right, the concept probability. Okay, we're not here to repeat calculus 1. Any question? All right. So the next topic, right, is about the CDF and PDF of a continuous random variable. So we don't talk about CDF much in discrete random variable, right? So remember, CDF stands for cumulative distribution function, right? And it's denoted as big F rather than small f of a random variable at a value. Okay. And it's defined to be probability x less than equal to little x. That's the definition. Again, with continuous random variable, the equality is irrelevant because, you know, but it's good practice to keep the less than equal to, because in more advanced courses or in general, a random variable can be mixed, right? And you have seen a mixed CDF before, right? Sometimes continuous, sometimes discrete. So you want to keep the equal, right? To just as a good practice. But anyway, right? In terms of the CPDF, it will be the integral from minus infinity to little x, right? Of f sub x of, let's say, u du. And again, right here, pay attention to the notation. X has already been used as the upper limit, right, for the integration. Therefore, when we write in the abstract, the integrating variable should be something else, like u. Okay? So you write x like this is kind of confusing because which x are you referring to? The integrating variable, which is a dummy variable, which will disappear, or the upper limit. Okay. For example, right, the CDF of a random variable at 3 will be the probability that random variable is less than or equal to 3, which will be, right, the integral up to 3 of the density. And here we can switch back to x because there's no upper limit to reserve the notation for. But because of this relationship, right, then by the fundamental theorem of calculus, if you differentiate the CDF, you will get the PDF. Okay. Again, there's a place for this, as we'll see. But per se, if you look at a single random variable, most of the time you don't really have to use for CDF. We'll show you, right? One instance where this is used, or one set of problems where the CDF is used, but not in a particular aspect of a random variable. Okay, so any question about the CDF and the PDF? So basically, right, CDF is a probability, but it's a very particular type of probability. Probability to the left, right? Probability that x less than equal to a value. Integrate PDF, you get CDF. Differentiate CDF, you get PDF. Say that like 10 times, right? Make sure you get the C and the P correctly. Yeah. And of course, right, things like this. Limit as x goes to infinity of the CDF is 1. Limit as x goes to minus infinity of the CDF is 0. We see that, right? Because if this goes to infinity, that's the total mass, so that's 1. If this goes to minus infinity, well, right, 0. Okay. Moreover, if you have a less than b, two values are less than each other, then f of b minus f of a represents what? This is probability x less than equal to b minus probability x less than equal to a. Well, pick your choice. You can just you can already do this in chapter 1 or 2, but if you want to be more clear here, you can represent it as a PDF. And since a is less than b, like that, right? But I mean, if you just check the logic of complement, things like that, this is really probability of a strictly less than x, less than equal to b. Any question? For example, right? So this is quiz 6, right? Quiz 6. So let's look at the PDF, right, that we just found. So 3/8 for x minus x squared, 2x squared. Find the PDF, find the CDF function. So the PDF looks like what? The PDF, right, looks like 0 here, right, and 0 there, right? And probably something like that. I'm not sure, symmetric, whatever, right? But probably is, yeah. Sorry, not 0, 2, right? But so that's a PDF, right? So you see with the CDF, then you need to kind of give 3 ranges of values: below 0, between 0 and 2, and beyond 2, right? So a piecewise function. So it's clear, right, that this is 0 for x less than or equal to 0, because the PDF is 0. Now, between 0 and 2, it will be the integral from 0 to x of 3/8 for u minus 2u squared du. Right, so f sub x of x is equal to 0 less than x less than 2. Which will be, right, 3/8. I guess we solved it before, right? 2u squared minus 2/3 u cubed. Sorry, 2x squared. Right? And finally, is 1. Let's check, right? When you plug 2 in here, you see that you also get 1. So, right? Oh, and I guess I forgot to tell you one more property, right? I think I said it before, but so 0, x less than or equal to 0, 3/8, 2x squared minus 2/3 x cubed, 0 less than x less than or equal to 2, and 1, x bigger than 2. So let's recap one more time, right? And we'll be done. So basically, the easy properties we see here that works. Limit goes to minus infinity is 0. Limit as x goes to infinity is 1. One more thing I forgot to tell you is it's going to be increasing, or more properly, non-decreasing, right? So basically, it can be constant, but it can only go up. It can never go down. And this would reflect that. And of course, right, at any point, if you differentiate, you should get back the PDF. All right. Okay, so let's stop here. If you have any question, I'll answer. If not, I'll see you on Friday.
Thank you.
Mhm.